If you want to review. Okay, these are all the formulas that you need to remember for ideal gas. So now we are under the topic kinetic theory of gases. This is the syllabus. During the 15 minutes break, you can try some of the question. Because it's good lah. These are called macroscopic properties, pressure, volume, temperature. It's good to, right? When we study about ideal gas equation, we are interested in macroscopic properties of gases, pressure, volume, temperature that we can measure. Give us a good description of gases in many different situations. Does not explain why gases behave this way. Where do you get this formula? Why gas behave this way? So we come to kinetic theory. Kinetic theory of gases is a theory which links microscopic property. Imagine that in the gas, there are particles there. The particle has mass, has velocity, has kinetic energy. Macroscopic properties of particles to macroscopic properties. So we use these microscopic properties to explain the macroscopic properties. On the basis of this assumption, it is possible to use Newton mechanics to show that the gas law, gas particles move with a range of speeds. So all matter is made up of particles. Particles can be atoms, molecules, or ions. Particles can be imagined as tiny billiard balls, right? Size about 10 to the power minus 10 meter. Particles are in continuous motion. Brownian motion is just normal in the syllabus. I just read through to understand what is okay. In the experiment, we see bright points of light moving with continuous irregular motion. The bright points are smoke particles in the scattered light. So the conclusion from this experiment suggests that the molecules of liquids and gases are in a state of continuous motion. The molecules of air frequently collide with the smoke particle at high speed to give Brownian motion. Right? We see bright speck. Right? We don't see the smoke particle. We see bright specks there. And the specks are moving in continuous motion. So it must be the air particle is moving and colliding with this smoke particle. Right? So that's the conclusion of Brownian motion experiment. Okay, we won't spend too much time on that since it's normal in the syllabus. Okay, so we started off with particle. We want to make assumptions, believe what it should be lah, right? So when our guesses doesn't come to the assumptions, approximate to the assumptions, then you can expect that it doesn't behave as what the kinetic theory will predict lah. So I written there for you, PINED, fine. Point molecule. The volume of molecule is negligible. You look at all these molecules, combine them together, push them into a volume, right? The volume is very small compared to the volume of container. So it means that the particles are very far apart. If they are very far apart, the intermolecular forces, I for intermolecular forces, the molecules are far apart, the intermolecular forces are negligible. The molecular forces are the forces of attraction and repulsion. When it's too close, there will be force of attraction. No? Then when it hits the wall, it will rebound off. Right? So these are assumptions that you have to remember. Number, there is a number of molecules even in a small volume, and then a large number of collisions occur at a short time. The average of many impact give a smooth pressure. Particles are in continuous motion. Right? This one is not accepted by Cambridge, right? But it has to be there. This assumption has to be there, because we are using statistic to in our derivation. So if it's a still particle, it doesn't work. Right? It has to be a lot of particles. But anyway, don't write this one. Write the other three assumptions. Memorize. Elastic collision. Molecules are perfectly elastic sphere that they undergo elastic collision. Right? No energy loss. No kinetic energy loss. D for duration. Duration T1 of collision is negligible compared with the time between collision T2. So we are not looking at the collision between particles. We are looking at a collision between the wall. So the time, the duration is the time it hits the wall of the container. And then T2, time between collision is it hits the wall, it goes back, hit the other side, and then comes back again. That is the time that you want. We call it T2, duration. Right? Duration is the time of collision with the wall. This is the time to hit the wall and return to hit the wall again. Okay, there's no way we can find T1. So that's why we can estimate T2. Right? We're not interested in the collision between particles, but with the wall of the vessel only, right? Or the wall of container. There's no way to measure the time of collision between molecules. Right? The collision of between molecules is there, but there's no way you're going to measure that. Pressure is due to collision of molecules with the wall, not collision with each other, right? Because we are interested in the pressure on the wall. So we are going to derive this formula. P is 1/3 nm V over C squared. Number of particles in the container, that's the capital N. M is the mass of particle. Right? Each particle has a mass, or each molecule has a mass. C is the speed of particle, any direction. And then this is a symbol for mean square speed, the whole thing. This whole thing, mean square speed. We'll go into more detail later on. V is the volume of the container. So that Nm, this is the total mass. This is the volume. So this becomes density. Okay, so what we are doing is we are first looking at a particle. Particle has a speed, and we let it collide with the wall of container in one direction. Then after that, we look at the change in momentum of the particle. Then from the change in momentum, we calculate the force on the particle. Then that's using Newton's second law. Then using Newton's third law, the force on the particle is equal and opposite to the force on the wall. Right? That's action and reaction forces. Okay, let us start. Right? We simplify it. In physics, we try to have as simple as possible our theory. Then if it works, it's good enough. Consider a cubic container, a cube, containing n particles, monoatomic, or mass m. Right? This particle has a mass m. Assume all the particles move in the x direction with the same speed. Right? All the particles move in the same direction with the same speed. Particles are monoatomic. Here we are interested in the particles colliding with the wall of the container. We are not interested in the collision between particles. Right? There's no way we are going to measure that. The pressure is because of the particles hitting the wall. Right? We're going to derive this formula. Right? If you find this is ridiculous, you can straight away replace this ux with u. Mean speed lah. Mean speed. T, time to hit the same side of the wall. Right? We are going to hit this wall, then goes back to hit the other side, and then come back again. That is the time. L is the side of the cube. Okay, so if it's moving, if the mass is moving with ux, then it has a momentum, mu. Right? So it hits this wall, it goes back and hits the wall again. So the distance traveled is 2L. So speed is distance over time. Right? Distance is 2L. Right? This is the time. Stop me if you want to ask question.
Okay.
Okay, just reviewing the same thing. Right? This particle has a mass. Has an initial speed. We take to the right as positive. And after collision, elastic collision, it rebounds with a minus u. Right? This is a velocity. Minus u means velocity in the opposite direction. Vector quantity. So initial momentum, change the momentum. Right? Final momentum minus initial momentum. So if we take u, then this also becomes minus u. So that's why we get minus 2 mu. Right? Distance travel is 2L between, so the time is 2L divided by u. Right? That's your total distance. That's a speed. Right? Because your time is distance over speed. Then we use Newton's second law. Change the momentum divided by time. Change the momentum. That one there. Right? Time is this one. So 2 and 2 can cancel off. And multiply by u, bottom, denominator, multiply by u on numerator. So the u and the u cancel off. So we got minus mu square L. So we have calculated for n particles, we just multiply by n. And then we use Newton's third law of motion. Force on wall equals to minus force on particle. Pressure on the wall. Right? We calculate this is the force, this is the force on the wall. So the pressure is force over area, total force divided by this area. Right? This area. So that's the force divided by area. So A times L is volume. Average pressure. Right? We just use average velocity. No? We average this one. No? Okay. You have derived this formula, but it's not perfect. We can modify it. Correct for the assumptions. You say assumption is not suitable. It's ridiculous. In general, the molecules can have a speed in 3 directions. So we replace our U with our C. Then 1/3 of the molecule will move in any of the 3 directions. So instead of U, we write U square plus V square plus W square. Right? Instead of U, we replace it with that. And then there's no reason to expect that they are going to be different. The mean speed in any of the 3 directions must be the same. So we put our U equals to V equals to W. So that's why we get this one equals to 3U squared. Right? And as we say, we replace our U with our C. So we are replacing with that. Okay, so complete replacement, we got from here, we get 1/3 U, 1/3 mean square speed equals to U square, mean square speed for in this in the X direction. Right, so we have got this formula. Okay with that, any comments so far?
Okay.
U is X direction, V is in the Y direction, W is in the Z direction. Kinetic theory states that the molecules of gas move continuously at random and often collide with the wall container. When a molecule collides with the wall of the container, it undergoes change in momentum. I'm just going over with you, reviewing what we have done. Right? Particles collide with the wall container, there's a change in momentum. That's how we derive that change in momentum. And then the rate of change in momentum means the force acts on the molecule. And then Newton's third law of motion, an equal and opposite force acts on the wall. That's how we get our force acting on the wall. Pressure is the average force acting per unit area as a result of impact of molecules of gas on the wall or container. We use pressure, total force divided by area. Okay, pressure of gas. It's a formula that we just derived. Right? This one is given in the formula sheet that you'll be given for your paper. You must know what the term means. Each of the symbol what the means. Okay, there's an alternative formula, but this one is given in the formula sheet. From this formula, we can see that pressure depends on N, number of particles in a container. Greater number of particles, greater pressure. C, the greater the speed of the gas, the greater the pressure. Mass of gas particle, greater the mass, greater the pressure. Volume of container, larger the volume, the lower is the pressure. At high temperature, the speed increases. Right? High temperature, we will show you the speed will increase, so pressure increases. Okay, so now we try to relate our what we have derived to temperature. But before we go there, let's look at some of the terms there. Mean square speed is the mean or average of the square of the speed of all the particles in a container. Right? So if there are n1 particles with a speed c1, n2 particles with a speed c2, and n3, n is the number, n3 particle with speed c3, and n particles with the speed Cn, then the total number of particles will be, we just add all the n together, all the n1, n2, n3, and nn together. So that's what it means. Mean square speed, right? Divided by n. Okay, so far?
Yeah.
Then root mean square, we just take the root mean square, that's all. Square root is the square root of the mean square speed. Root mean square speed is greater than the mean speed. Right? Compare the mean speed, but root mean square speed is greater. Okay, average translational kinetic energy of a molecule. You need to know how to derive this one. Right? This is average translational kinetic energy of molecule. C is the speed of particle. M is the mass of particle. The whole thing is mean square speed. K is Boltzmann's constant. T is absolute temperature. So we can see from here, where T equals to 0, the ideal gas has a 0 kinetic energy. The substance is 0 kinetic energy or minimum internal energy for solid and liquid. Right? For ideal gas, no kinetic energy if T equals 0. But for solid and liquid, remember there's potential energy, there's kinetic energy. Kinetic energy may be 0, but it still have potential, it still have internal energy. It still have potential energy. Right? Recall this formula. Right? We derive this formula using Newton's law of motion. This one we derive experimentally. Okay, comparing the two equations, these two equations, P and P equal, so we get this new equation. N and N can cancel off, V and V can cancel off. So we get mc squared is 3 kT. So average translation kinetic energy of a molecule, we just times half on both sides. We got this equation. Average translation kinetic energy of molecule is proportional to temperature. Absolute temperature is a measure of the mean kinetic energy of the gas molecule. Right? From this formula, by measuring the absolute temperature, we know the average kinetic energy of the molecule. Average translation kinetic energy of a molecule, right? Right. This equation shows that the mean kinetic energy is directly proportional to thermodynamic temperature. Kinetic energy of mixture of gases does not depend on mass of gas at the same temperature. Right? Don't worry about this one. Kinetic energy depends on temperature alone. So even if you have a container with a mixture of gases, temperature is the same, kinetic energy is the same. Right? Of course, if the mass is different, it will affect the mean square speed. Okay, but the kinetic energy is still the same. Still the same depending on the absolute temperature. Okay, so this is for one molecule, kinetic energy for one molecule. Total, we just times n. No? There are n molecules. So we get, right, same. We just multiply by n on this side, and that side there, we get nkt or 3/2 nRT. For ideal gas, there is no intermolecular force between the particles. Right? So the sum of potential energy equals to 0. Energy is totally kinetic. Internal energy of an ideal gas is total kinetic energy of particles in random motion. Memorize it. How we define our internal energy of ideal gas. And it's given by 3/2 nRT. There's the internal energy is proportional to absolute temperature. Right? So it's mainly kinetic energy. An increase in temperature T of the gas means an increase in total kinetic energy of the gas and thus increase in internal energy. The internal energy of an ideal monoatomic gas is directly proportional to absolute temperature. We are just going over this formula, that's all. This is true regardless of molecular structure. That means it can be, this formula is true whether it's monoatomic or diatomic or polyatomic, many atoms in the molecule. However, the expression for you will be a bit different for gases that is not monoatomic. What this is saying is that it will affect this one, right? But it won't, it will still depend on temperature, right? Still depend on temperature. But that one you don't need to worry because you are only interested in monoatomic molecule. Okay, so internal energy is this formula. So what does it mean? It means that if the absolute temperature of the gas is doubled by heat transfer, for example, from 200K to 400K, then the internal energy is double. Right? Because 10 more minutes is double. That means it's twice as hot. The kinetic energy is double. Right? Absolute temperature double. Kinetic energy double. This doesn't apply to the Celsius temperature, only to absolute temperature, since its 0 point are not referred to the 0 point of energy. Molecules in gases move about randomly at high speed. They collide with one another and with the wall of the container. Collision with the wall gives rise to pressure of the gas on the container. Okay, that's how the formula we have derived. So when we put a thermometer and heat the liquid, what's going to happen? Right? When the thermometer is placed in a container, the molecules collide, right? The liquid molecules collide with the collide with the bulb of the thermometer, imparting the kinetic energy to the thermometer. So that's why the temperature rises. At higher temperature, the molecules move faster with greater kinetic energy. They give more kinetic energy to the bulb and the mercury rises higher. Hence, the reading of the thermometer is an indication of the kinetic energy of the gas molecule. Where's kinetic energy and temperature? Kinetic energy is proportional to absolute temperature. That's the formula that we are looking at. As the temperature is double, the average kinetic energy per molecule increases. Double also lah. Air is a mixture of several gases, for example, nitrogen, oxygen, and carbon dioxide. In a sample of air, the kinetic energy of nitrogen molecule is the same as the kinetic energy of oxygen and carbon dioxide, right? Because all are determined by temperature. If they have the same temperature, they have the same kinetic energy. Carbon dioxide molecule have a greater mass. Carbon dioxide heavier than oxygen molecule. Since the kinetic energy is the same, oxygen molecule will move faster than carbon dioxide, right? Greater mass. This one will be smaller if the temperature remains constant. That's what this one means. Okay, so we have got all this formula. Right? Root mean square speed. Root mean square speed is directly proportional to the square root of the absolute temperature. Root mean square speed is inversely proportional to the mass. For a mixture of gas in a container at thermal equilibrium, right? Same temperature lah. The gases are all at the same temperature. The heavier gas has a smaller root mean square speed. Right? That's what it means. Heavier root mean square speed smaller. Okay, so you can have your own mind map to summarize what we have learned to help yourself lah. Oops, sorry. Okay, so that's the mind map there. To summarize all the things, to help you to memory, all the things that you have to memorize. Right? And these are the formulas that you need to know how to use. And this one is given a formula sheet. The others you need to memorize. Okay, let's do some question. Remember, we are going to be cut off at any time. Okay. State the basic assumption of kinetic theory of gases. This is 2010 November, paper 43. Okay, can you remember the basic assumptions of kinetic theory of gases? Can? Point mass? What does the point mass mean? Can or not? That one you have to memorize. Right? Sometimes it can be 2 mark and it can be 4 mark, depend on the question. So this one require you to have 4. Particles behave as elastic identical spheres. Volume of molecule negligible compared to volume of container. Time of collision is negligible compared to time between collision. No forces of attraction or repulsion between molecules. Okay, so 4 marks. So particles are in continuous random motion. Sometimes they will accept this one. Okay, so this derivation use equation for the pressure of ideal gas to deduce the average translational kinetic energy of a molecule of an ideal gas is given by the expression R is the molecular gas constant, molar gas constant, and A is the Avogadro's constant, T is the absolute temperature. So basically, you have to use these two formulas. And then right, put them as equal. PV, so this one equals to that. And then kinetic energy formula is this one. So this one, right, you need to replace this one N with N over Na. Then the N and N can cancel off. 3 can transfer to the other side. And then together, kinetic energy half. We just half here, half here. Now. So that's why we get our 3 because of this 3. And RT and RT. Then N is there. Right? This half. That's the half of kinetic energy. And replace this N with N over Na. Right? N and N can cancel off. So we get our equation. Okay or not?
Teacher, by the way,
Yeah.
have you sent me the doc for this?
The what?
The document.
This one is under, I do guess, under matter. I send you 3 together. I haven't sent you this PowerPoint yet, but I will send you after today. No?
Oh, okay.
Anyway, you can try to do the other question during your time short break. Review through. Okay, it's just to show you how to derive it. No? This one can get it from formula sheet. This one you have to memorize. So PV and PV cancel, that one equals to that one there. It's the alternative way of derivation. And replace the N with N over Na. So that's what we get. So N and N can cancel off. And then kinetic energy formula times 3 here, times 3 on this side, times 3 on this side. That's what we get. Deuterium nucleus and a proton collide. The nuclear reaction occurs represented by the equation is one. They can combine two parts of topic